to organic compounds. Today we'll be focusing primarily on the functional group alkanes, ANE, representing single-bound hydrocarbon molecules. So we already kind of went through all of this in the last video, so I'm going to move on to the material. Alkanes, ANE, alkanes, single bond. They represent any general formula where we're just going to have carbon and hydrogen. That's it. The only two atoms in the compound are going to be carbons and hydrogens, and they're all going to be singly bound. So they're all going to have this general formula. So it's kind of a cheat. When you look at a formula, you can use this quote-unquote method to help you determine without having to draw it if it would be a single, whether it's going to have only single bonds or if it would be something like an alkene, ENE, or an alkyne, YNE, where it had double or triple bonds. So the N represents the number of carbons in the molecule. So if this was 4, that means that the hydrogens would be 2 times 4, which would be 8 plus 2 more. So this would be C4H10. We can see with methane, there's a 1 here, right? So this would be 1, and then this would be 2 times 1 plus 2, which would give us 4. That's how we're getting CH4. Methane, and we'll talk about naming today as well, is the simplest of the alkanes, and it's a natural gas. It's also your farts. From there we can get ethane and propane, and we go in this pattern, and we'll learn how we go from meth, eth, prop, and down the line. But what it means is 1 carbon, 2 carbons, 3 carbons in a chain. After 3 carbons, which is propane, we go to butane, which is 4 carbons. Butane is where things start to get a little tricky. Last video we talked about the concept of isomerization and isomers, and we learned about structural isomers. So we're going to talk about how butane has some different isomers to it. And to be able to do that, we need to talk about 2 different types of alkanes that exist. We have normal alkanes, which are going to be these just straight chains, and then we can have branched alkanes. And the trick with these is to just run your finger down the line. Even if this was all twisted, and we'll look at different examples where it's twisted, you'll be able to know if it's a normal alkane if you can touch all of the carbons without lifting your finger. Over on my branched one, I can't do that. I have to lift my finger at some point to touch the other carbons. So that will be your kind of guide to help you decide whether you have a branched alkane or a normal alkane. So let's look at the difference between some of the butane. So like we said, butane is going to contain 4 carbons. So here's our normal butane. That's why we call it N-butane for normal. 1, 2, 3, 4. I don't have to lift my finger. I can touch all of the carbons. This is isobutane, and it's isometric. There's a central carbon, and then there's a CH3 branched off of that central carbon in each direction. Here's my central carbon, 1 carbon, and I can go here to 2 carbons, but then I'm going to have to lift my finger to come over here to touch this one, and then I'm going to have to lift my finger again to touch this one. It's easier to look on here. I can go 3 across this way, but then I'm going to have to lift my finger to come touch this one. Or I can go 2 this way, and 1 over, right? I could go like that. And I didn't lift my finger at all to touch those 3, but I'm still going to have to lift my finger to come over and touch this one. So that tells me that this is a branched isomer of butane. So how is the following compound and the structure shown as it is classified? So take a minute, pause. I really encourage you, and you might feel silly, but run your finger on your screen and go through and try and determine whether this is branched or normal. From our first video, you should know whether this is written in the condensed or expanded formula. So I'll pause here, try and answer it. This is normal and expanded. So expanded, remember, shows all the covalent bonds represented. And if I start here with my finger on this carbon, I can touch all of the carbons without lifting my finger. Even though it's bent, that's fine. I can still touch all of them without lifting my finger, so this is a normal alkane. Okay, so when we have alkanes, A and E, single bonds, we have to remember that single bonds can rotate. So think back to when we had lab, when we were still meeting in person, and you were building those model kits, right? We can rotate a single bond. It's kind of like wagon wheels, right? So if this was the front axle of a wagon wheel, right? And this carbon is the center of the wheel, and then these three things around it are the wheel, and there's three things around it on this wheel. I could twist this wheel in this direction, and I could twist this wheel in this direction, and they're independent of each other. That's what we call free rotation. When we have double and triple bonds, we don't have that anymore. It locks it into position. So what we end up seeing is we know that electrons, atoms, right, even though to us they may seem solid, we know that they're in constant motion. So they're going to try and find a arrangement, or a conformation we say, where they're going to be the least hindered. And so let's look at this. We have 1, 2, 3, 4 carbons. 4 carbons, so this is a butane. And I can touch all of them without having to lift my finger. So I know this is a normal butane. But let's look what's going on. At these 2 carbons, that means around this carbon I have 2 hydrogens and a CH3 group, which we call a methyl group. On this one I have 2 hydrogens and a CH3 group. Hopefully you recognize that the CH3 group is a lot bigger than just the individual H's by themselves. So think about it. If I had both H's pointed up, that means these 2 big groups are kind of squished and having to, make room for each other. But if this were to rotate around, I could have one on top and one on bottom, or away from each other. Now these really big groups have more room to kind of spread out and not have tension on each other. So there are all sorts of different conformations we see for N-butane. This is 2 of them. Here's where both of those groups were up, like in that first image. Here's the CH3 group, right? It's quite big. So there might be a little bit of kind of tension between these 2. And here, right, here's the 2 C's that were highlighted in blue on the last page. And here are the 2 C's highlighted in blue on the previous page as well. In this case, one of the CH3 groups is pointed up and the other one is pointed down. So we can see that this gives everybody a little more room than this does. So I'd like you to pause here and try and figure out this problem for yourself. Pause your video, go through and answer it. So the top 2 molecules are both normal alkanes containing 5 atoms. So again, they're normal because I can run my finger along the entire molecule and touch all the carbons in the chain without lifting my finger. Same with this one. Even though there's a bunch of little twists and turns and bends to it, I'm still never having to lift my finger. The bottom 2 are branched. Think about this. I can go all the way across this way, but then I'm going to have to lift my finger and come up and touch this one. Or I could go all the way across this way, and I'm still going to have to come over and lift my finger to touch this one. Or I could touch these 3, and still going to have to come back over to touch these. Same with this one. I can go all the way this way, I could go all the way this way, but I'm still going to have to lift my finger to touch the last one. So these would be branched. Which of the following pairs of structural isomers and which are simply different representations of the same molecule? So for you to answer this question, you have to remember what a structural isomer is. So think back to our first video where we talked about the idea of the little Lincoln log house where you had the same parts, but the house, the structure is different. So I would encourage you to pause the video here and give it a shot. So these 2 are the exact same molecule. What we see is, you may be going, well, they both have 5 carbons, but if we look at it, if I numbered this 1, 2, 3, 4 this way, the 2 carbon is the one that has the CH3 group poking out of it. I could very easily start my 1 over here and go 1, 2, 3, 4, and then the 2 would still have the CH3 group poking out of it. This would be like if I took and built this as a model and then I just flipped it. It would still be the same compound. If we look at these 2, again, we're going to be using this numbering system to kind of help identify which carbon we're talking about quite a bit. When I number this way, 1, 2, 3, 4, 5, the 2 carbon has the CH3 group on it. And if I went 1, 2, 3, 4, 5 this way, the 3 carbon has the CH3 group on it. And you're like, well, up here we switched it. So let's say we started with 1 here. 1, 2, 3. The 3 carbon still is the one with the CH3 group on it. So there's no way that I could kind of rearrange, flip the molecule around in a way where it looks exactly like it did before. So these would be structural isomers of each other. Same formula, different arrangement. So I'm going to pause the video here and give you an opportunity to go through and figure out this problem. These are our structural isomers. Okay, so up until this point I told you didn't have to worry about naming. Now you have to worry about naming. If you have worked in a field before where you already are familiar with some names of compounds, they might be the what we call common name. And for the purposes of this class, we are going to focus primarily on the IUPAC naming system, which stands for International Union of Pure and Applied Chemistry. Basically, it's a set of rules so that everybody can name the same compound, whether you're in Germany or Zimbabwe or Antarctica or in California. Wherever you are, everybody knows what compound you're talking about because we all name it the same way. Before this system, different parts of the world named compounds differently. And as you can imagine, that got very confusing. So some common names are still kind of around today, and that's all right. And we'll look at some of those examples, but primarily we're going to focus on the IUPAC naming system. So there are 3 parts to naming an alkane, A-N-E, in the IUPAC naming system. There's a prefix, a root, and an ending. The prefix will denote the number of identity of each group attached. So we'll talk about what that means. The root, this is the easiest part. This is the longest chain of carbons that you can make. And I guess a little kind of note to add here is the longest chain of carbons where I don't lift my finger. Okay? So even if it's a branch compound and it's got 5 carbons in it, but you can only touch 4 of them without lifting your finger, the longest chain of carbons in there is 4. And lastly, the ending is going to denote which functional group it is. So right now we've only talked about alkanes. So the ending of all alkanes will be the same. And hopefully you've picked up on this. All alkanes end in the same ending, A-N-E. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. They all end in ane. So the ane tells me that they're a hydrocarbon with all single bonds. This meth, eth, prop, but, pent, these are the words for the root. Remember I said the root is going to be the longest chain of carbons in the compound where you don't lift your finger. Now these are all normal alkanes, so the chain is the longest they go. And we have kind of a naming system for how many number of carbons there are. So before, when we had di, tri, tetra, things like that, it's a little different when we name it for carbons. So you'll need to learn these new roots. Meth means 1. Eth means 2. Prop means 3. But means 4. Pent, like a pentagram, means 5. Hex, like a hexagram, means 6. Hept, with a PT, is 7. Oct is 8. Non is 9. And dec is 10. We will only go up to 10. Those are the ones I'm going to expect you to be able to know. Anything higher than that, and I would provide it for you. So you may be going, okay, so I have a root and I have an ending. Where the hell are the prefixes here? So we're going to talk about those in a minute, but I just want you to be comfortable with what we have going on so far. So these non-alkyl groups, what the heck are these? Oftentimes we will see extra little doodads on our chain, that root, right? We said the longest chain of carbons where we don't lift our finger. But we know when we have branched alkanes, we have carbons that aren't being counted in that root. So how do we name those? Or what if there's a fluorine or a carbon, or a chlorine or a nitrogen group or something like that on there? These are what we call non-alkyl groups. And basically they're like little decorations on our chain. And they have naming systems as well. So if we have a fluorine attached to the carbon chain, it would be a fluoro. This would be the prefix. A chlorine would be a chloro, a bromo would be a bromo, Iodo, an NO2 group is called a nitro group. An NH2 group is called an amino group. So let's look at this. Let's start with something really simple. Let's do just a branched alkane. So when we look at this compound right here, we go, okay, I can go all the way here, but then I have to lift my finger, or maybe I go all the way here, and then I have to lift my finger. So no matter how I look at it, I'm going to have to lift my finger. So this is a branched alkane. So when I'm naming this compound, the first thing I can do is look at it and go, ah, this is an alkane. There's no double or triple bonds. It's all single bonds. So I know my ending is going to be A-N-E. Then I have to figure out a way, how am I going to count this, where I figure out the longest chain? And sometimes what you initially think might be your longest chain, you're going to have to double check. So sometimes your numbers won't be right the first time. So let's start here. If I start here and I go 1, 2, 3. Okay, that's probably not the longest chain. If I start here and I go 1, 2, 3, 4, 5. Okay, that seems good. What if I went 1, 2, 3, 4, 5? That same number there. If I start here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so it looks like no matter how I slice it, 5 is the longest chain, which means when I look at my roots, I know pent means 5. So I have some sort of pentane. So now I have to determine how I'm going to represent that extra carbon, that extra CH3 group, that isn't being counted in the chain. Now, the way I numbered it here, 1, 2, 3, 4, 5, means that that extra carbon is this guy right here, on the 2. This CH3 group is on the 2 carbon. That is not being counted. If I started with 1 here, 1, 2, 3, 4, 5, it would be on the 4 carbon. Or if I went 1, 2, 3, 4, 5 this way, it would still be on the 4 carbon. So my options are to have it be 2-methylpentane or 4-methylpentane. A CH3 group is called a methyl group. That's the alkyl name for a CH3 group. So 2-methyl or 4-methyl. The rule will always be in the IUPAC system that we want to go for the lowest number possible. So 2 is lower than 4. So we would call this 2-methyl, that's my prefix, pent, my root, ane, my ending. Let's look at something a little more complicated. When we have multiple branches, we need to start organizing how we're going to name everything. So when we have multiple branches of the same type, so for instance here we have 2 methyl groups. I'm going to modify the name to be di, tri, tetra, penta, and we'll separate each position by a comma. And then we need to list those branches alphabetically. So if I have dimethyl, it's still going to be the M. The di, tri, tetra don't count towards the alphabetical name of it. So let's look at what we got here. We have to find the longest chain first. So I could go 1, 2, 3. Nope, that's not going to do it. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Okay, let's try backwards just to make sure we're not missing anything. 1, 2, 3, 4, 5, 6. Nope. 1, 2, 3, 4, 5, 6. No, okay. So I'm not finding a way to do this where I get a longer chain. So this chain up here is the longest chain I can get without lifting my finger. I see that is all single bonds, so my ending is going to be ane. And because 7 is the longest chain, it's hept. So I have some sort of heptane. So that takes care of all these guys up here. But I still have to account for these ones down here. So I look and I see a CH3 group and a CH3 group. So I have 2 methyl groups, which I would say is dimethyl. And then I have this CH3CH group. Hopefully you're looking at this and you're seeing that this is an isopropyl group. It's a propyl group, 1, 2, 3 carbons in an isometric formation. So this would be 4 isopropyl, 2, 3 dimethylheptane. The reason the isopropyl comes first is I comes before M in the alphabet. Remember, we don't put the di as part of the alphabetization. So I want to give you a moment to go ahead and draw this compound right here. 3-ethyl, 2-methyl, hexane. So I will let you know most students have an easier time going from the word to the drawing than going from the drawing to the word. But you will have to know how to do both. So I'll pause the video. I encourage you to pause it and actually draw this out. So the first thing we have to do is we look at our compound and we say hexane. All right, A and E is our ending, so we know it's all single bonds. And hex tells us that the longest chain in there is 6 long. So I'm going to draw out 6 carbons. We're told 2-methyl, which means we have a methyl group on the 2 carbon. And we have 3-ethyl, which means there's an ethyl group, 2 carbons long, on the 3 carbon. So that takes care of all the wording. So what goes on the rest of this compound to finish it off? We need to add our hydrogens. So we go through and add them, and we now have our compound 2-methyl, 3-ethyl, hexane. Go ahead and answer this answer this question. Correct answer is decane. The longest chain that I can make without lifting my finger is 10 long. So go through and make sure that you can count that out. Can you name this compound? 2,2,3-trimethylpentane. So let's find the longest chain. 1, 2, 3, 4, 5 carbons long. 2, 2, 3. Trimethyl. Now, you may be going, why do I have to say 2 twice? Because we need to identify that this carbon 2 has 2 methyl groups on it. So we count for each of them. 2, 2, 3, trimethylpentane. The last topic that we're going to talk about of our alkanes before we move on to some other things are cycloalkanes. So these are alkanes that are cyclical. So they'll kind of make boxes or rings. We use the prefix cyclo to represent that it is cyclical, and it just will be added on to the regular alkane name. So to give you an example, here are some cycloalkanes that exist. Cyclopropane, 3 carbons, prop, but in a cyclical form. Cyclobutane, 4 carbons. Cyclopentane, 5 carbons, 6 carbons, so on and so forth. Now, those carbons can have, those cycloalkanes can have decorations on them, and we have to go through and give them naming just like we did before. Again, we want to give the lowest number possible to everything. So when we look at this cyclopentane, we see that we have an ethyl group up here and a methyl group down here. So if I numbered it in this direction, 1, 2, 3, I would have 1 ethyl, 3 methyl, cyclopentane. Now, if I started here and made this 1, 2, 3, I would have 3 ethyl, 1 methyl. And you want to try and make it in order. And it's a ring, so it doesn't matter if I started here or here. I want to try and have it in order. So that's why the ethyl group is the 1, because alphabetically E will come before M. Now, let's say you went and numbered this 1, 2, 3, 4. That means I would have 1,4-methyl cyclopentane. 1,4-methyl cyclopentane is higher numbering than 1,3. So we want to go with the lowest number possible, and we want to try and have it go in order. So, go ahead and try and name this compound. Hopefully you can see that we have 1, 2, 3, 4, 5 carbons in our ring. So this is a cyclopentane with a methyl group on it. So it looks something like this. We have a cyclopentane with this alkyl methyl group. Now, if there's only one group on there, start with this as your 1. That way it's the lowest number possible. Don't start with 1 up here, because then this would be 1, 2, 3, or 1, 2, 3, 4. If I make this the 1, then it's 1-methyl cyclopentane. Can you name this compound? This is 1-ethyl 3-isopropyl cyclohexane. 1-ethyl, E, comes before isopropyl. 1, 2, 3, isopropyl in the 1, 2, 3 position. Which of the following is 1,4-diethyl cyclohexane? Hopefully you were able to identify it couldn't be either of these because it's a cyclohexane. Neither of these are rings. Now we have to look at it and go, okay, 1, 4. Well, 1 and 4 on a hexane would be on opposite ends of each other, right? 1, 2, 3, 4, or 1, 2, 3, 4. Okay, so these are both in the 1, 4 position. And we're told diethyl, which means I have 2 ethyl groups. These are both methyl groups. Ethyl is 2 carbons long, so this would be the correct answer. So, the last thing we're going to talk about with cycloalkanes is the idea that we can have some conformations still occur here. So remember earlier when we talked about rotation and conformations in alkanes because they're single bonds, we don't have as much flexibility in a ring because the ring kind of rigidifies the molecule. There isn't as much free rotation, but they can kind of flip-flop a little bit. So when we have things like a cyclohexane, it will have 2 different conformations, a boat and a chair. Now, I did not come up with the names for these. I think they're pretty stupid. I don't really see a boat or a chair, but that's the name of them. But we'll go through it. Things smaller than 6 carbons in the ring don't have too many conformations just because they're so small and rigid, but we'll see these different conformations mostly in rings of 6 or more. So cyclopropane, cyclobutane, cyclopentane, they're kind of stuck in those positions. But then we have the chair and the boat of cyclohexane. That's 6 carbons long. I guess you can kind of see that this is a boat. It's like if you took your palms and you had your the ends of your palms facing each other so your wrists are touching, and you put your fingers in both hands up, it makes like a cup, like a little boat. I guess this looks like a lawn chair. I guess like a reclining lawn chair. It's more flat. This is definitely a cup. This is more of a like twisted flat structure, and that's why it's called the chair. Like I said, I don't really agree with it, but I wasn't around when they named these, so I didn't get a say in it. So, because of this rotation, or I guess these conformations that we see in rings, it's not like the free rotation we see in a normal or branched alkane, right? We know that, like the wagon wheel, they can rotate freely. In ring structures, even though they can, go boat or chair, things like that, they're stuck. That's it. That's all they can do. They can't rotate infinitely. So they have what we call stereoisomerization. Things can be stuck up or down, and that's kind of it. And that they aren't structural isomers because the arrangement, who's attached to who, is still the same. But unlike in a linear structure, now we have a ring where there's a top and a bottom to the ring. So is something pointing up top or is something pointing down? So we have what we call geometric isomers, and these are defined as cis and trans. And molecules with restricted rotation around a carbon-carbon bond, for example, in a cycloalkane, we'll also see this in our triple and double bonds, differ in their 3-dimensional arrangement. So unlike a structural isomer, where they have the same formula, but they are attached in different ways. Geometric isomers have the same formula and are attached in the same way, but their 3D arrangement in space is different. So we'll look at this, and the two different types of geometric isomers are cis and trans. Cis meaning same, trans meaning opposite or different. So right, in a single CH bond, in a single CC bond that's linear, this can rotate freely. But when the CC bonds are all kind of tied up in a ring, it's not possible for it to rotate anymore. So here's a perfect example of that geometric isomers. We have a cyclopentane. Let's start with numbering here. We'll say 1, 2, 3, 4, 5. So we would call this 1,2-dimethyl cyclopentane. When we count this, 1, 2, 3, 4, 5. So this is also 1,2-dimethyl cyclopentane, but they're different, right? In this case, think of the ring like a pancake. This has got both methyl groups pointing down on the pancake on the bottom side. This has one methyl group pointed down and one methyl group pointed up. So they're different. These will have different types of properties to them. They will react differently. They will have different shapes to them. All sorts of different stuff will occur. So we need to have a way to define the difference between these two. And we do that by using the geometric isomer prefix. Cis means they are on the same side. Trans means they are on opposite sides of this bond. That's what we're talking about. We look across the bond. The bond is here. We look across the bond. They're on the same side across the bond. Across the bond, they are on opposite sides across the bond. So, I would like you to try and draw and name the different structural isomers for dimethyl cyclobutane now. Cyclobutane is going to be a square, right? 4-carbon ring. Now, we told you dimethyl, so there's a couple different options here. We could have the methyl groups be on both on the 1 carbon, the 1 and the 2 carbon, the 1 and the 3 carbon. You may be going, well, why can't it be on the 1 and the 4? Well, the 1 and the 4 would be the same as it being on the 1 and the 2. Does that make sense? I could go 1, 2, 3, 1, 2, 3. It's the same either way. So 1, 1, 1, 2, or 1, 3 are my options. Again, you may be going, well, why can't it be 2, 2? If it was 2, 2, then we would just start with our counting of our number 1 here. Or if it was 3, 3, we would just start with our counting of our number 1 here. So that takes care of the different positions they could be in, but we need to figure out the geometric isomers. So there's quite a few of them. If we have the 1, 1, it doesn't matter because they're not across a double bond. So it would just be 1,1-dimethyl cyclobutane. There's no isomer for this one because it's not going across a bond, a CC bond. It's all on the same carbon. For the 1, 2 and the 1, 3, we do have geometric isomers. We could have trans 1,2-dimethyl cyclobutane or trans 1,3-dimethyl cyclobutane, right? Across the carbon bonds, right? When we look at the ring, they're on opposite sides, top and bottom. Or we could have the cis version of those, where they are on both on top or both on bottom. Can you name this compound? Trans 1,3-dichlorocyclopentane. Dichloro, we have 2 chlorines. They're on opposite sides of the ring. One's pointed down, one's pointed up, so they're trans. We count out the numbering, 1, 2, 3, 4, or 1, 2, 3. 3 is smaller than 4, so we have trans 1,3-dichlorocyclopentane. This is the end of our second part of Chapter 11. I would strongly encourage you to start doing your homework for this section and looking at the resources available on our extra help page.